I want to finish today this chapter 4, so I hope I have enough time to describe all what I want to describe. This section 5 was not in the original program of the chapter, but as I just said, I think it should be included here. So so far we have described in some detail how quantum field theory core spacetime is formulated. We started with the classical theory, describing what are the important ingredients. The important ingredients for us is a linear equation, a space of solutions, and a product defined on the space of solutions, this Klein-Gordon product. And from it, we were able to build a quantum theory, so a quantum representation of the commutation relations by choosing one subspace of positive frequency and the associated subspace of negative frequency. That was the key element. And we were describing that there are many ways of choosing that, so there are really many different quantum representations, many Fock representations. And we learned how to relate them. The relation is given by this Bogoliubov transformation. And in the last class, we really realized that mathematically, most of them are inequivalent to each other. That is a big surprise, but it seems that one can still do physics if we restrict for a finite number of observables and for observations with some finite accuracy, no matter how small it is. I want to close this chapter by telling to you in which circumstances we really do have a preferred representation. So for arbitrary spacetimes, we don't have a preferred one. But there are some spacetimes, some special spacetimes for which a preferred representation exists. And they are what we call static and stationary spacetimes, which are close but not the same. So therefore, we focus attention here in this section in a spatial family of spacetimes. The spacetimes. Those are static and stationary. So let me start describing static because it's easier, and then I will tell you. I mean, I'm sure you already imagine what happens here. What happens here is that for these spacetimes there is a time-like Killing vector field, so the metric is symmetric in a time direction, and therefore one can use that time to define positive and negative frequency modes, and that is going to provide a preferred representation. So in short, this is what is going to happen, and so let me just describe it a little bit more. So just to refresh your memory, a spacetime. So spacetime is a manifold, 4-dimensional in our situation, with a Lorentzian metric. We say it's static if it admits and everywhere time-like Killing vector field. Let me call it T mu. So, and we have this Killing vector field. And so if I stop here, this is only stationary spacetime. The static spacetime has some additional conditions. And there exists a family of hypersurfaces, of spatial hypersurfaces. Spatial hypersurfaces, which are in fact Cauchy hypersurfaces, labeled by some parameter t, which is going to be the parameter along the Killing trajectories, orthogonal to the Killing vector field. So two conditions. There is a Killing vector field, and one can really foliate the spacetime with hypersurfaces which are orthogonal to a Killing vector field. This is a static spacetime. Schwarzschild is one of these spacetimes. So here, the idea is that, So here one can choose coordinates, at least locally, such that the time coordinate, let me call it t, runs along the killing trajectories. The killing trajectory. So what I mean is that, take the killing vector field, it's a time-like killing vector field, take the integral curves of the killing vector field and choose your time coordinate running along those curves. Then the fact that the statement that T is a killing vector field translate in that the components of the metric on that system of coordinates are T independent. So you just choose adapted coordinates to the symmetry. So then the coordinates of G mu, so the components, right? The components are independent of T. If one can do that with any killing vector field, just using adapted coordinates and the metric doesn't depend. And one always finds these adapted coordinates at least locally in any spacetime. So the statement is that one can take advantage of this time-like symmetry to define a preferred notion of positive and negative frequency. So we can take advantage of this time translation symmetry to select a preferred notion of vacuum and one particle Hilbert space. And it arises by it arises by choosing S plus. Remember, if I give you an S plus, I give you one particle Hilbert space and a Fock space and a notion of vacuum. So by choosing S plus, the subspace of the complete space of solutions span by solutions phi of t that have positive frequency with respect to the killing time. So if you take the time derivative, you plug minus omega I the field with omega larger than 0. So just exactly the same as we did in Minkowski spacetime, but now using the time t. So not a big surprise. And as I said, this defines for you a preferred notion of preferred one particle Hilbert space, therefore preferred notion of quanta, and a preferred vacuum. And so this is the same as we did in Minkowski spacetime. The only thing is that in Minkowski spacetime we had many inertial times that we could use. To a boost, you get another inertial time. In fact, you have a 3-parameter family of inertial times, where the 3-parameter family is the 3-parameter family of boost you can make. You can make a boost on the x direction, y direction, and z direction. So you have a 3-parameter family of inertial times in Minkowski. Here the difference is that we only have one time. You know, the space-time is arbitrary, except that there is a direction in which so a time like Killing vector field. So we are using that specific time to build the quantum vector. And so, you know, in words, what I'm saying, maybe I should write it. So, in words, this positive and negative frequency decomposition provided by the Killing, time like Killing vector field, is the structure that allows us to define a preferred quantization. So, in stationary spacetimes, they have a time like Killing vector field that that's it. So stationary spacetime is that they admit a Killing vector field, but they don't have. There are no hypersurfaces for which it is orthogonal. That happens when you have some kind of rotation or twist in the space-time, like, you know, like for a rotating black hole in Kerr space-time. You know, there is a time like Killing vector field, but there are no hypersurfaces which are orthogonal to the Killing vector field. So it's a weaker condition compared to the time. Still, they are time symmetric, but there are no hypersurfaces to which the Killing vector field are orthogonal. So for example, spacetimes having some rotation on them or twist, like, you know, in Kerr black hole, etc. The statement here is that, you know, because this hypersurface doesn't exist, one cannot guarantee that this Fourier expansion is well defined, in fact. Warranty that, you know, this Fourier expansion with respect to the time, the Killing time t, is well defined. You go to a book of mathematical, you know, a book of analysis, Fourier analysis, or spectral decomposition of differential operators. For instance, you can see Fullin's book of quantum field theory. He has a good summary book. You will see the details why, you know, why by dropping the assumption that these hypersurfaces exist, it is not guaranteed that Fourier transform along these Killing trajectories are well defined. So mathematically, one cannot justify this construction, but nevertheless, I'm not going into the details. Just tell you that nevertheless, Oesterkar and Magnon in 1975 showed that the idea can be made precise. So this idea still works in that case. And this is essentially what I want to say. And, you know, I'm sure you find it logical. If you have a time-like symmetry, you can define this preferred representation. And a small remark, I think the point was raised last day, is that, you know, note that a space-like Killing vector field doesn't define a preferred representation. However, a time time-like Killing vector field? Yes. So we only need a time-like Killing vector field. So this is telling to us that that this decomposition, this vacuum state notion of quanta is closer to time than to space. This is what we call this space. It's a space of positive frequency, and which is attached to time. It's nothing really surprising, but it's good to have that in mind explicitly. Any question?
It's a good question, but so I'm confused about what does dynamic space-time means if time itself is a coordinate?
Say it again.
So we're talking about static and stationary space-time.
Mm-hmm.
So as opposed to this, what is the meaning of dynamic space-time? If time itself is a coordinate, then what is it changing with respect to the space-time?
But that is a general question in general relativity.
Yeah.
General relativity, time. What do you mean by time? What do you mean by dynamics of the
Yeah,
space-time?
because space-time is known for all time because time
Right.
is a coordinate. So
Right.
what is it changing?
I mean, so here in our, I can ask the question, separate two questions, in GR and in our context. In our concept, the metric is given to us, and we study the dynamics of quantum fields on that space-time. And the quantum fields will evolve. What is static or stationary is the metric, is the space-time itself. Like in Minkowski space-time, this is of course evolving, even though the metric is not evolving. In GR is a different question. In GR,
But I mean, what we are discussing is based on the properties of the space-time. Right? We're saying that in these space-times, we have this preferred notion of.
right.
So that is not clear to me. Like, that what's the difference between a dynamic space-time and static?
I mean, the only difference is that in dynamical spacetimes, with any time coordinate you want to choose, no matter which time coordinate you choose, the metric is going to change in time. So there are some spatial spacetimes in which that doesn't happen. The metric on some spatial direction, like Minkowski, or like in a black hole in Schwarzschild, there is static, the black hole is over there, nothing happens. The spacetime is non-trivial because you have a horizon, you have gravity strong, close to the horizon, weak, far from the horizon. That doesn't change with time, at least with some time-like trajectories. So those spacetimes are easier to study. Still, you can study dynamics of fields on that. The fields will evolve, even though you can fall inside the black hole. So this is what we mean here. Is that your question?
I'll discuss with you later.
Okay. And a different topic is what happens in GR, how we define dynamics in general relativity, but that is a whole different thing. So this is simple, and as you could already anticipate. So where I want to spend more time is in what we call particle detectors. And this normally, as I said before, is introduced in the chapter of Unruh effect, but the notion is more general. So let me introduce it here, and then I will use it in the Unruh effect. So, and my motivation came from a question a few weeks ago, which is the following. We are here in this chapter and in chapter 2 in Minkowski defining particles in a bit mathematical way. We choose the composition of the space of solutions in a positive frequency part, negative frequency part. We choose a basis. Associated with the basis, we define creation operators, and whatever those guys create on the vacuum is what we call particle. That, a student can be not completely happy. Particle, I know what it means. It hits me or whatever. How is this relation associated with the more intuitive or physically obvious notion of particle? Can we complete that gap? Can I provide for you one more step that brings us for this abstract definition to a more pedestrian or more intuitive or physical definition? The answer is yes, and this is what we are going to do with particle detectors. So in this section, I'm going to introduce what we call a particle detectors in field theory, and in such a way that that what we in particle will be what this apparatus is able to detect. So this is what our normal intuition tells us. references, classical references for that is Unruh in 1976 and the bit in 79. I will restrict myself to the simplest particle detector, and you can make it more complicated if you want, but with this is enough. A simple particle detector can be modeled by a quantum mechanical system coupled to the field. That is coupled to the field. The field. Of course, this is essential. If it is not coupled to the field, it cannot detect particles of the field. Of course. To keep it simple, let's choose it having two energy levels. U1 and E2 larger than E1. So a fundamental level, a fundamental state and an excited state. And so two energy levels with respect to a free Hamiltonian HQ. So let me call HQ the Hamiltonian of our quantum mechanical system. So the total Hamiltonian of our system will be the Hamiltonian of our Klein-Gordon field, the free Hamiltonian, plus the free Hamiltonian of our quantum mechanical system, which is modeling the particle detector, and an interaction Hamiltonian. So this is free Klein-Gordon Hamiltonian. This is the free Hamiltonian and this is the interaction Hamiltonian. So what I have to, in order to specify the particle detector, I have to give you that Hamiltonian. It's going to be very simple. So the statement is that H can be modeled by a simple coupling like this, some small coupling constant, G, the field operator, and simple couple between the detector, between the field and the detector moving along a trajectory x of t that we choose to agree with the killing trajectory. So here M is just sum operator in the Hilbert space of the detector that we don't need to specify if you want. That we don't need to specify. So this is one of the simplest models of particle detector that you may have. So you have, these trajectories of symmetry, the orbits of the Killing vector field.
Slightly bigger.
Slightly bigger. Somebody's complaining.
No, I can't.
You can read. Okay.
Are we still working in static?
Yes, I am still in stationary spacetime. Maybe I didn't emphasize it. So I work because we have this definition of particles in stationary spacetime. So we have these Killing trajectories, and we have a detector that I modeled by a simple mechanical system with two energy levels: the fundamental state and the excited state. And I write this coupling, the simplest coupling I can imagine. Some coupling constant, of course, some operator for the quantum mechanical system, and the field operator. And this can be as simple as you can imagine. It can be whatever you want. I don't even need to specify what this M operator is. Is the simplest operator. This is enough to define a particle detector. Of course, I am idealizing it. So idealizations I am doing. Let me make some remark. Idealization. We are assuming the detector is point-like. So because I am coupling the detector and the field along the trajectory of the detector. But I am assuming the detector is just a point. So you can you can define a more realistic detector with some, just say that the Hamiltonian is going to be some interval in space, and if you want in time, where the coupling constant may also change with time, so you can switch the detector on and off adiabatically if you want, and the detector, now M has some x, phi some x, and now I add here f of x, where f of x has information about the profile of the detector. So function accounting for the size of the detector. I could do this, in order to be more realistic, but we don't need to do this. Just to tell you that one can be more realistic and incorporate a detector with some finite size, just having some interval with some function that describes how big is the detector. So you give me an apparatus with some size and with some resolution, and these f's account for that. But with this is enough for describing the physics that you want. Of course, when you have, every time you have a detector or something which is an idealization of zero size, we will have a delta function at the end of the calculation. So we just have to know that this delta function, which is divergent, is because we are two different. Otherwise, we will have an integral of the delta function on some compact support function. So now that we have this simple model for a detector, the detection of a particle will be, a transition from E1 to E2 plus the field changes the field, how do I say? The field being reduced in a quantum of energy E2 minus E1. So when that happens, we can say that we have detected a particle. We have this detector moving in the field. The field is in some state. The detector starts in the ground state, and suddenly the detector jumps to the excited state, and the state of the field decreases in one quanta with energy given by the jump. So then we can say that we have detected a particle. And now we know physics, and we have integration Hamiltonian, and we can compute what is the probability of this to happen, or even we can also ask the other way around. If the detector is in the excited state, what is the probability of decay to the fundamental state? So we can do all the computations that we want. So let me show to you how to do that, or at least give to you the main steps to compute that. So let's see how this materializes in equations. So first, I'm going to describe absorption. I think so. Yeah. Let me describe absorption. So first of all, we will assume that the initial state of our system, our system is the field and the detector. We will assume that the initial state of the system is the detector in the ground state. And I'm going to choose for simplicity that the field is in a state with n quanta in the mode j. So state of the field with n j quanta in the mode j. I choose an eigenstate of the number operator for simplicity. I could choose whatever you want, but the equations will be cleaner. I could choose also a vacuum or something simpler, but this is enough for what I want to show. So what we want to do, we want to let the system evolve, both the field and the detector, and compute the probability of finding it in the state E2 n prime j after some time. This is what we want to do. So take this initial state, evolve the system dynamically, and after some time compute what is the probability of finding my state in a state in which the detector has been excited. If you know quantum mechanics, you know how to do this. Any guess?
We just evolve it by influenced by the Hamiltonian.
Right. So every time we have Hamiltonian, it's easier to work in the interaction picture. So better to work in the interaction picture. So remember, operators evolve with the free Hamiltonian states with the interaction Hamiltonian. This is the way that we work in the interaction picture. So in particular, the initial state as a function of time will be usual the exponential of the time order time interval of the Hamiltonian with respect to the initial state at time equals 0. This is the interaction Hamiltonian in the interaction picture. I need an H bar here. And normally what we do is to develop this exponential. You know, it's 1 plus the exponent plus higher order in the coupling constant. If we stop at first order in perturbations, this is enough. So I'm going to compute that probability at first order in perturbations. I forgot to say it, but at first order in perturbations. So this is what I want to compute. Where the interaction Hamiltonian in the interaction picture depends on time, and it's just the interaction Hamiltonian that I wrote before over there, where the operators evolve with the free Hamiltonian, because operators evolve with the free. So it's going to be G, the M operator. No, the M operator is an operator in the Hilbert space of the detector, so it evolves with the free Hamiltonian of the detector. H bar, the free Hamiltonian of the detector time, e to the minus I H bar, the free Hamiltonian of the detector t. Time, the field operator that we know how to evolve it in time. So it's the Heisenberg operator we have been working on for a few times right now. So this is what the interaction Hamiltonian is.
Is H sub I sub n's different from the normal interaction?
Yes, it's the interaction Hamiltonian in the interaction picture.
Oh, okay.
So in the interaction picture, any operator evolves with the free Hamiltonian. So what I take is the interaction Hamiltonian and evolve stuff with the free Hamiltonian. So once we have this, the probability amplitude we are looking for at first order in perturbations, first order in perturbations. So it's amplitude of moving from the initial state, which is the fundamental state, to the excited state. So all I have to do is to take this line and plug the final state over there. Right? So here I have two terms. This times 1, this times this. I am forgetting hands. So because the final state is different from the initial state, the one will give me 0, because this has E2 and this has E1, and they are orthogonal to each other. So only the second term will contribute. So what I will have will be the final state just let me jump one. So I H bar integral in time from minus infinity to infinity if the constant, if the apparatus is on for the whole time, then I will have, this is coming from here, I will have E, let me put it explicitly, Nj E2, which is the final state. Now let me put all the operators that they have e to the I Q T M0 e to the I H Q T and the field. The field is always along the trajectory of the detector times the initial state. So this is an operator for the detector, so it only will hit a state for the detector. This is a state for the field. We only hit the state for the field, the operator for the field. So this will become this is just e to the I am forgetting h bars. H bar. This is just H bar E2 T times E2. This guy and this guy just give me E1 e to the minus H bar E1 T. So I just have minus the infinity dt G E2 E1 e to the I H bar E2 minus E1 T times Nj prime, the field along the trajectory of the detector you know how to compute this. The only thing you have to do is to write the field operator as a sum in modes. So the field operator now can be written as sum j. The modes, remember that because now we are in a stationary space-time, they are the spatial part, sorry, the temporal part is given by a positive frequency mode, and the spatial part is given by some spatial function that I don't need to specify, plus the admission conjugated. And you know how this A acts on Nj is going to, I should use here a different bubble. Okay. So AK is going to decrease the number of quantum one and etc. So this step is trivial. So let's go to the probability. Are you with me?
Yeah,
People with me?
so, why didn't we evolve phi in the while writing HI interaction?
Why we what?
Why didn't we evolve?
Yes,
phi
it's evolved. Time is there. But what I said is that this is the standard Heisenberg operator we have been working on all the time. So the Heisenberg operator is precisely that. The field evolved with the free Hamiltonian. So it's this is already evolved, right, with the free Hamiltonian. So if you want, it's the field in the interaction picture. So, so just one thing, the trajectory of the detector, the detector trajectories, the detector trajectory in our adaptive coordinates, is x of t, is just t fixed position. The detector moves along one of these killing trajectories, and we are adapting coordinates to it, so the position of the detector is fixed. The only thing is that the time is changing, and it changes with it. So x is just some fixed x naught. So the probability that we are looking for, probability of jumping from the initial state to the final state, will be given by the square of the probability amplitude. So all we have to do is to square that. I don't write, how to compute this because it's trivial, so I left to you as an exercise. Just complete this step, which is nothing because I did 95% of the computation. So this is going to be g squared 1 over h bar. I have to choose to put time 1 and time 2 because I am taking the square of the time interval, so there are 2 intervals in time. E to the I over h bar delta E t1 minus t2. I have to raise this line, sorry. Now we have the T2 m naught E1 squared, and now we have the part that depends on the field, so let me add it here in a line. It's a bit long, so we have 2 terms, then j delta nj minus 1 comma nj prime into the I omega j I know this is a bit long, but that's the way it is. So it's long, but you shouldn't complain because I was thinking in leaving this as an exercise for you. So we are close to the end. So there are 3 lines in this equation. First line, second line stops there, and 4 lines, right, and the 4th line. So now we have 2 time intervals, t1 and t2, but if you pay attention, everything depends on t1 minus t2. There is no plus everywhere, So it is smart to change variables to t1 plus t2 and t1 minus t2, and so change variables to t plus t1 plus t2, t minus t1 minus t2. The integral in t plus is divergent because nothing depends on t plus. So we have an integral from minus infinity to plus infinity of a constant that diverges. So, but that is almost, that is natural because, you know, that is assuming that the detector is on forever for an infinite amount of time. So it's normal that, you know, if the answer is non-zero, it's going to be divergent. So what we want to do is to compute the probability per unit time. What is the probability of being excited per unit time? So normal, since the detector is on forever. We can do two things. We can, as I said, compute the probability per unit time, which is what I'm going to do, or, you know, turn off, on and off the detector adiabatically. So that is another option. So have g a function of time, so that, you know, it's zero, it becomes non-zero, and then it's off again adiabatically, so we don't disturb the system. That will also give you a finite answer. So we are interested in probability per unit time. Let me call it PIF dot. So this is just the probability rate, and what I have done is just get rid of the integral in t plus, and I mean, I'm going to write one more equation because it's just that, you know, there are too many things. It's quite long. So let me write one more step, and that's square, and then we have also the spatial part of the mode square. I didn't say it, but I think it was obvious that this is just the spatial part of the mode. The mode had the mode functions as a temporal part, which in this case is e to the I omega t, and this is just the spatial part. And then we have two terms corresponding to the two terms in the last line. The one is e to the I delta E over H. I am defining delta E. Delta E is E2 minus E1, and is positive by definition. So delta E is a positive one. Minus omega j t. And then you have here nj delta nj minus 1 n prime j. And I have another term. Let me put some space here. J delta nj plus 1 nj. Okay, let's see what physics is that given to us.
Is this in plus or
Where?
these two terms?
Yeah, that should be.
There is a plus, right? There are two terms. There is a plus.
And both the integral integrals are dt minus or minus dt plus r.
Yes, that is right. In principle, I had two intervals in each term. I take
taken per unit time, so that one goes away.
I take read. I only t minus appears. So I divide it by the integral in d plus, which was divergent. So I compute the rate, and I only take with that integral. So remember, we are computing the transition from this to this. So we have two terms. I mean, probably it's just easier to give you to do the calculation of the sum. So we have two terms here. This term, two intervals. This interval and this interval. What do you think is the value of this interval? Let's do first this one. This one is just a delta function because it's the integral of an exponential, so it's a one-dimensional delta function of delta a over h plus omega j. Would
Is the first term in p dot raw e2 and e2 again, or is it e2?
is E1, sorry. But look at this term. Frequency is positive by definition. This guy is positive by definition. So this is zero. They can never be. You have the sum of two different quantities. This is never going to be zero. So this delta function is zero because they should have correspond. So only the first term contributes. The first term is again 2 pi delta function delta minus omega j. And this goes in the right direction because that tells us that whatever the frequency of the mode of the field that is involved in the transition has to be equal to the energy of the two levels. So we are in the right track. So just let me. We have the solution right now. So just let me write it in a single line. So I can also sum on. I don't know. So the probability rate from 1 to f is the following: 1 over h bar g squared e2 this again square times 1 over 2 omega j nj and this delta function. This Kronecker delta times so this is the expression that we were looking for. So first of all, we have this part here. This is the part that depends on details of the detector. So if the detector is very good, if it is very bad, if whatever, this is just the part that depends on the detector. This part depends on the mode of the field that we are choosing, and the probability rate of excitation. So this is the absorption rate. Is different from zero only if nj is larger than 1, larger than 0, because we have 0 particles. This is the number of particles initially present in the field. If we don't have particles in the field, the detector cannot be excited. So we need at least one quanta. The final is this delta Kronecker tell us that the final state has one less quanta than the initial state. If the final state is nj minus 1, and the energy of the quanta which has been lost is exactly the same as the difference of energy. So this equation quite clearly is telling us that the process of excitation comes together with absorption of one quanta of the field with energy delta. So this is what we were expecting.
So in the expression that you have boxed, where did the 1/2 omega j come from?
Something that they forgot.
Yeah, from those.
Sorry.
Oh, over there.
It's coming
Okay,
from
yeah,
here.
yeah. Okay.
That I forgot. Yeah. Sorry. So let me add it, multiply it 1/2 omega j. I forgot from here. And here there is no square. There is no root square anymore because this is the square of these ones. So here we have root square, and we are taking the square. So here I shouldn't have root square. So the root square that I had here should be removed.
And where did the 2 pi go?
The 2 pi, nowhere.
Okay.
Thank you. Very long expressions. Yeah.
So one of the 2 omega j's go away. We have 2 omega j square now. The root is not there.
So
No.
no. So we had here root square, just one,
Yeah.
and we are taking the square. So root square goes away, and this is what we have: 1/2 omega j.
Yeah.
We are not taking more square. So one can do the analogous computation of the emission rate. So for the emission rate, we have as the initial state an excited band with some particles in the field, and for the final state, we have. So I'm not going to repeat the computation. So if you do it yourself, you are going to get something very similar. G square 1/8 bar, the properties of the detector, which are normal in case we have some super selection rules or whatever. The spatial mode functions again. And 1/2 omega j, and at nj plus 1 delta nj plus 1 n from j I think I want to have to write in black. motion rate, emission rate. Sorry. Rate of a detector following a killing trajectory. I didn't write this following a killing trajectory there, but of course it's the same. Can we interpret this equation for me? So now we have nj plus 1, where nj is the number of initial quanta that we have in the field. Is that expected?
Yeah, because we're increasing the quanta in the field, decreasing the energy of the detector, and we're requiring that the two are the same.
Right, but this is this delta.
Yeah.
This delta function tells you that that the final number of quanta in the field is going to be 1 more than before. So the detector gets excited and emits 1 quanta with the energy that we want. But what about the numerical factor multiplying? This is multiplying.
Spontaneous plus stimulated.
Exactly. So this is spontaneous. This is stimulated emission. It is spontaneous. So this is what we will expect. The more quanta we have initially in the field, the more likely is to emit 1 particle, and this is what in quantum mechanics we call stimulated emission.
So a detector following a killing vector field would be different from a detector sitting on Earth, right?
Yes. Yes. So that will be a different detector. So what I have computed is in a stationary spacetime how a detector measures things if it is in a killing trajectory.
Okay.
In a detector here in Earth, if you consider that the gravitational field of the Earth is important, then it's not stationary. You are accelerating it.
Yeah.
We are not an inertial observer. We are accelerating with 9.8 meters per second squared. Right. But in our lab, we neglect the effects of gravity, and we consider ourselves as inertial. So this is a model of particle detector that you use in the lab.
Okay.
Because the curvature of the space-time here is really negligible.
Okay.
That technically speaking, we are not inertial, of course. We are not. Sorry. This guy is inertial. Almost, if there is no atmosphere. Anyway, so this is a bit long, but I think that the final expressions are very cute. Are what would you really expect? Something coming from the detector, something coming from your field, and the logical things that you expect. So they speak very well about the physics that is going on. So what I want to say here is that this equation and this equation really suggest us to interpret the field theory in terms of particles. This is telling to you that I am emitting 1 quanta. This is telling to you that I am absorbing 1 quanta. I have stimulated emission. I have created emission. The quanta has energy that I am detecting with my detector. So these equations is what invite us to interpret the field theory in terms of particles. They are telling to us that what we really have there is particles with energy given by that. And all our intuition about particles in field theory is coming from this kind of detection, because this is what we measure in the lab, and really is suggesting us that is the right physical interpretation. And so we have to keep in mind that where is that coming from, and that is quite useful to create that intuition, but also keep in mind that this particle interpretation is quite limited to situations in which only an ambiguous notion of particle exists. In general, a field theory is not a theory of particles. So use the notion of particles intuition whenever you can use it, but understand that that is a limited concept that only works in certain circumstances, and a field theory is really a field theory. One of the facts that is telling to us that we live in a field theory is this notion of spontaneous particle creation. Spontaneous de-excitation. This is not really spontaneous. It's because we have a field and the detector is really interacting with the field. But in this particle interpretation, we have to make up this new concept to accommodate that interaction. But to me, it's just telling to me that, that we have our fields. Okay, so just tell you that this is a nice interpretation whenever it's available, but it doesn't have any fundamental support from a field theory because a field theory in curved spacetimes, in an arbitrary spacetime, doesn't have a natural particle interpretation. And this kind of expressions will be very useful, or similar expressions will be very useful in the Unruh effect to interpret what is going on. Just to advance a little bit in the Unruh effect, in Minkowski spacetime, we use the time translational Killing vector field. In Minkowski spacetime, there are a lot of Killing vector fields. We have a 3-parameter family. You can take any time-like direction inside the light cone, and that is a Killing vector field. But we also have the boost. The boost, if you see the vector field generating boost, is also time-like, and it's also a Killing vector field. So normally we define particles in Minkowski using the time translational Killing vector field. But you can say, no, I'm going to use the other one, or I'm going to put a detector in that other Killing vector field. That corresponds to a detector which is accelerating with a uniform acceleration. But there is also a Killing trajectory. So what that detector would measure in Minkowski vacuum. So you define the Minkowski vacuum with the standard time translational Killing vector field, and ask how many particles you would measure if your detector is following the other Killing vector field, so it's accelerated. That is, the answer will be non-zero, and that will be the Unruh effect. So, but we will see that. So in the last 5 minutes, let me just write for you some expressions for these probability rates, which are quite useful.
Wait, so I do have a question about interpreting this. So that spontaneous creation of particles.
No, this is a spontaneous emission. So we have a detector which is excited, and if you leave alone, it will emit.
Okay, so the detector emits particles.
The detector is excited, and it emits a particle spontaneously, and the final state will be the detector is in the ground state, and the field has one more quanta.
Okay, so this comes from the excitations of the detector itself, sort of.
So what we have, we have studied 2 processes. The first process, this is the E1, E2. The first process is the detector was here, and we had a lot of n quanta. What we found is that after some time, we have some probability of having the detector there, and nj minus 1 quanta finally.
Okay.
This was this computation. This computation is the detector starts as here, and here we have n quanta. After some time, the detector is here, and we have nj plus 1 quanta. So the detector has decay spontaneously, or or induced. We have both emission rate. We have spontaneous emission or induced emission, and the field increases the final number of quanta is the initial plus 1. So the detector has emitted 1 quanta.
Okay, so to make a big step away from what we've done with scalar fields, it's sort of like saying you could have pair creation on a photon.
But this pair creation of particles, this is, this is just the field by itself.
Right.
So,
yeah, but
that is a different history.
That's sort of what that's sort of the closest analogy in terms of what you would actually have in a particle detector.
I don't understand what it is.
Well, but so we don't actually have scalar fields, right? Other than the Higgs field, right?
Who knows?
Yeah. So I'm trying to think like what this corresponds to physically.
If you want to do it with photons, if it is clear for you, just take an electromagnetic field. It has some photons on it, and you have some detector which is measuring now electromagnetic quanta, and you will have the same. If you measure a photon, you have a detector ground state. When the light in the detector pumps, you have detected a photon, and there is a less one less photon in your field. If your detector is excited, like an atom, hydrogen atom is in an excited state, it goes down and emits a photon. This is what we are describing.
Okay.
But this particle creation of fields is something different. So this is just a detector measuring how many quanta we have.
Okay.
And if you want, my goal here was to give you an operational way of defining particles. You can call this the process of measuring a particle, and this is your definition. It's a physical way of measuring or defining particles, if you want, in an operational way.
But if it's in a curved spacetime, then if you go to the curved spacetime, these particles that we detect may not have, will not be the eigenvalues of the.
Right. This is in a stationary
In a stationary
spacetime where you
spacetime,
have
this is
this preferred right. But in a generic spacetime,
You can.
right. A detector can tell you there are particles, but a different detector following a different trajectory can tell you that there are not.
No particles.
But you have to do everything carefully because I was using the fact, in order to define energy levels, I was using the fact that the spacetime is stationary. If you don't have time-by-Killing vector fields, you may even have difficulties in defining energy levels.
Because they are not eigenvalues of the.
Right. So all what you do is really tied to your trajectory. So just to finish this chapter and give you some demonstration, let me finish with a subsection called transition probabilities, which is what we have described. And 2-point function. And all what I want to say is that there is quite elegant way of writing all these two transition probabilities in just one single expression, which involves the 2-point function. And we could guess it already from what I raised. From what I raised, you could realize that if you sum on the final, if we only care about what happens with the detector, and we sum over the final states of the field, all possible final results,
Over J?
over n prime j. So we take this and we sum over n prime j. So the only thing is that this delta is going to disappear. Nothing else happens. But in the expression before, you can see that the 2-point function arises by that sum. So let me do it. So we are going to derive an elegant and compact way of writing in a single expression the probability rate of emission and absorption. And now we're going to be more general, and I'm not going to assume that the initial or the final states are eigen states of the number operator. So here I was assuming a definite number of quanta. Now let me assume any generic initial and final state of the field. So we know that the probability amplitude, all the time we are talking about first order in perturbations. Of the transition. So we have transition that goes from some initial state of the detector, given by an I, some initial state of the field, to some final state of the detector, some final state of the field. I'm going to do it for either I f being 1, 2, or 2, 1. So I'm going to do it for absorption or emission. So just a single expression. Where alpha and beta are generic states of the field. Is we go from I to F and alpha and beta. The first column, I'm just repeating what the expression that I wrote before. This is the probability amplitude, dt. J into the I h bar EI minus EF T and EF and not EI beta alpha. So this is what we wrote before. And the associated probability is going to be the square of that. So we have to take the square. This times the complex conjugated. And now we have the integral t plus, the integral t minus. Before, in the previous computation, I jammed this step, but if you take this and multiply by the complex conjugated is just turn this around, so you have this product.
Is it h bar squared or h bar in all our earlier expressions?
No, before it was h bar because another h bar was coming from this computation. But I didn't write it down explicitly. So now the statement is that if you sum over the final state of the field, so over the final state of the field, so imagine that you just want to know what is the probability of excitation, no matter what is the final state of the field. You don't care about. You just want to know when it's excited to the network of the field beta. Then what do you think is going to happen? This time sum over all beta is just the identity in the Hilbert space. Using that the sum over all states in the Hilbert space of this is the identity, you get the 2-point factor. I am finishing. I should give some name to this matrix element because I'm tired of writing. T plus dt minus e to the I h bar initial minus e final t minus times what I'm calling the 2-point function in the state alpha. This is a quite interesting expression. I'm going to write one more like this, another short one. G. This is alpha, the field X T2. It really depends on T2 and T1. The field T1 alpha is the 2-point function in the state alpha. And this guy depends on T2 and T1, or in T plus and T minus, both. I can write T plus and T minus if you want. In the previous subsection, I was doing the integral in T plus, because all what was here only depended on T minus. But now in general, for an arbitrary alpha, it's not guaranteed that this guy only depends on the difference between T1 and T2. So it only depends on T9. That is not guaranteed in general. This is why I have box here. Now let me assume, so let me tell you what happens in the particular case in which this guy only depends on the difference. So if G happens to depend only on T1 minus T2, on T minus, then we can, and this is going to happen in most of the interesting situations, like in the Unruh effect that will be true. So let me just tell you what happens. That doesn't happen in general for any alpha, but would be useful for us. We can write the probability rate so we can divide by the integral in f plus, and this is going to be the integral in t minus e to the I h bar g plus, sorry, ei minus ef t times g alpha of t minus. So this is a very compact expression to compute both emission or absorption. Remember that we have sum over the final state. So this is the sum over the final state of the field. But I and F makes reference to the initial and final state of the detector. So this is a nice expression to compute the absorption or emission probability. Just as a, it's kind of Fourier transform of the 2-point function. And it is valid for both the emission, this will be positive, or absorption, this will be negative. And one of the cutest facts is that in addition to be quite compact and be valid for both emission and absorption,
what is T?
G,
T.
T, so T minus, sorry, T minus.
Thank you.
T minus, thank you. T minus is what appears there. So, if you see this integral and I ask you compute the probability rate of absorption or emission of the system, then you have to do this integral. All you have to do is the integral of the 2-point function. But this is an exponential, complex exponential, so one could use complex techniques like the Cauchy theorem. You will have, what I would do is to extend T minus to the complex plane, this integral is the integral here. Now I have an exponential here, which is an I. So if I, imagine that this is positive, the case of emission, this is positive. So if I take t going to I infinity, I times I give me a minus, and this is going to cancel, give me a 0 on this integral. So the absorption probability is going to come from the poles of the 2-point function. So the poles here give me absorption. You can do the same for emission. The poles of the 2-point function here, poles of the 2-point function in this branch will give me emission. So we will see in a particular case how one can obtain the probability rates of the absorption or emission as the poles of the 2-point function on the upper complex plane or the lower complex plane. And I think that is quite mathematically nice. So the poles of the 2-point function contain all the information about absorption and stimulated emission and induced emission also. I just want to leave the comment here, and you will see it how I apply it in the particular case of the Unruh effect. So in the Unruh effect, rather than using this expression, I will go here, I will identify the poles, and I will tell you, summing all these poles, I get the probability rates of absorption. So with one single expression and just counting poles of the 2-point function, I get the effects that I want. Okay? So no more physics here than what I described before, just nicer maths, because we have the 2-point function, which is the key element of the field, and a compact expression.
In absorption, EI minus EF would be less than 0.
In absorption, EI will be 1, E2 will be 2, so that will be negative.
So it should be...
This will be negative in that case, smaller than 0, so where I need here is, I need here minus I, so minus I times minus I is 1, and I have negative with something very, very big.
So shouldn't this be opposite? Like more than 0?
No, I think you're right. So absorption, this is, right, this is emission. This is absorption. Thank you. Or wherever it has to be to work. If you write it down, there is a way in which it actually works. So and I find this expression quite nice. So this section closes the chapter, and the goal was to give you this additional, this more computational, physical definition of particles, just using particle effects in stationary spacetimes, and give you these expressions, which will be very useful for the next chapter. So this chapter closes if you want, the first part of the course, in which we have settled down the theory. So now we are ready to apply the theory to practical applications. So we will apply to the Unruh effect. I already did one class of the Unruh effect because this was planned in the next chapter. Now everything will go faster. Then Hawking effect, inflation and the prediction of primordial perturbations. And let's see, what else? Any questions?
If we were to sum over J, which is different modes, why didn't
Final J. Here we can do it. I could just sum over final, so over n prime j, so this will disappear. This will give me 1. That's all. I didn't do it, so you can see explicitly that the final state has one more quanta than the initial state. So you have that.
No, I'm saying, so nj is for one particular mode, one
Right.
particular field.
Exactly.
So if we consider different modes,
If you consider in the initial or final state. But this tells us that only the modes for which the frequency is exactly, only the mode with the frequency is exactly the same as delta A over E is
if we
going to
consider
contribute.
the mode which is omega j by 2, that should also give me the transition if 2.
No, but then you need more physics than what we are considering. For the simple for the simple interaction that I draw, all of this may happen. This double requires interactions a bit more complicated. So here only, because we are, this in fact comes from nj prime. This was in our computation, and this has a plus a dia. So this guy can only differ in one quanta, cannot differ in two quanta.
But this guy has A and A dagger for all the moves.
Right. Right.
So
But
if we consider sets of initial and final state that would give us the detection, then we should consider all the moves.
So I could repeat the exercise using, this was emission, so using A2 to E1, using here any state alpha and any state beta. This is what I have done here. This is generic. But still, this will select transitions, will select one single mode with energy given by that gap. I agree that I did this computation for a particular case in which this was an eigenstate of the number operator, and this another one, just for pedagogical reasons. You can do it in general. You can do the exercise. It's just repeating this a bit more complicated. You will see that you are constrained by one single quanta. Only one quanta of the field is going to be emitted or absorbed. Those with energies given by